So yeah, one of the main takeaways that we took from yesterday's lesson is that if you see this phrase right here, at least one, that's going to tell you that we need to kind of think through this and maybe change our angle on how we view this problem. So if it was, what's the probability that we get no diamonds or all diamonds, then we can approach it kind of a straightforward way. That means we have to get, if it's all diamonds, we have to get a diamond, then a diamond, then a diamond, then a diamond. All right, that's pretty straightforward. If it's no diamonds, we get no diamond, no diamond, no diamond, no diamond. Pretty straightforward. Also, but now this is at least one. So it doesn't matter if we get 1, 2, 3, or 4. So now we have to think of it in the other direction. So 1, 2, 3, or 4 diamonds, they're all okay. The only thing that's not okay is getting no diamonds at all. So I want to get the complement of the failure condition. So that means I need to find the probability of not getting a diamond. And we just put that superscript C, that means complement. That's another way of saying not getting a diamond. Not getting a diamond, and not getting a diamond, and not getting a diamond, and not getting a diamond. And that is the only way we fail in this scenario. So if we fail at that, then the complement is going to be the probability that we succeed. So there we go. You can see it's a lot of complements in this. It's a very nice probability problem. All right, so each probability of not getting a diamond is going to be the opposite. So if we have a 1 in 4 chance of getting a diamond, we have a 3 in 4 of not. So I can say this is going to be, well, first of all, before I do that, it's going to be 1 minus. So this complement right here, I can rewrite it as 1 minus the probability of not diamond. I'm going to do this just to the 4th, you know. I know that's not the right way of writing it, but I'm saving myself a little bit of time. It's this thing again. Okay, so what I want to do is I want to find the probability of not getting a diamond. Like we just said, it's 3 out of 4, so 0.75 to the 4th power. And when we do that, we will get D as our answer. Okay, if you do want to come back and see this, we can look at this again or a problem similar to it. All right. So we're going to be looking at some specific new rules today. We got contingency tables again. That's going to come into play. Conditional probability, general addition and multiplication rules. So that's what we have to look forward to today. Maybe you already read about it. So maybe you're already kind of anticipating this. Okay, general addition rule. We're going to start with this one. And the question is, why doesn't the addition rule work for non-mutually exclusive events? And you can see right here, it's good that we've been seeing these diagrams. Now you can kind of see, if they're mutually exclusive, there's no chance that A and B can both happen. So now we can think of these as area. So the area of A plus the area of B, it's just adding 2 circle areas together. That's not a big deal. We can do that. But when they are not mutually exclusive, and you can see there's a possibility that both could happen, we have this overlap region. If I just add circle A's area and circle B's area, I'm double counting this area. So now I need to subtract the probability that A and B both happen. And we can avoid that with this one because the probability of A and B is 0. So basically it would be a -0 right here that we don't need to worry about. Okay. And I think this is just restating what I went through a second ago. Okay. So if you want to go back and look at the presentation, that was really restating what I already just talked about. So we have the general addition rule when we want to get rid of that overlap area. Oh, that's it. So this, and for right now, I do not know for sure if this is on your AP formula sheet. We're gonna, you know, we're gonna do a brief field trip, and I'm gonna find that out for you real quick, because I know a lot of stuff that's on your AP formula sheet. I cannot remember that one. So my field trip, you can't see what I'm doing, but I'm pulling up the formula sheet real quick. Pretty soon, I'm gonna be switching over to the formula sheet quite a bit to show you what's on here. So there we go. Luckily, you can see this is on the AP formula sheet right there. So you're good to go. Now, this is everything that we learned from our first 2 units, or first 3 units, right here, or whatever. And there you go. So this is something else we're going to talk about today, but the general addition rule is available. Let's go back to the presentation and we can move forward. It's good to know what's on there. And so I just pulled that straight off the formula sheet. So what does this even mean as far as in practice? Here's what we've got. We've got two-way tables. This is going to come into play from time to time. So we already have our marginal, No, okay, it's not on the slide. So the marginal distributions are right here because they're on the margins of the table. Don't forget that. And then the conditional are right here in the middle. And we're actually going to be talking, and I'll throw this term out later, it's conditional probability. So it's going to help you remember conditional probability comes from the middle of a two-way table. And we'll, of course, get to that. So we're going to use similar ideas from just what we learned already about two-way tables. So we're now going to think of this as these as probabilities of an event. So the probability of liking snowmobiles right here is liking snowmobiles. It's going to be the marginal totals. So I'm going to skip all the way over here. It's 105 out of 160. And the probability of not liking snowmobiles is going to be down here. And that's this next one. I'm going to take this 55 out of 160. And we can just use the table totals in that bottom right cell. Okay, so the marginal totals are where you get the basic probabilities. But then we can get conditional probabilities within that table itself. So probability of liking skateboards among people who like snowmobiles. So first of all, we call this conditional because, and we already talked about this in the past too, so it's a rehash. On the condition that someone likes snowmobiles, so only looking at this row, because it says among people who like snowmobiles, what's the probability of liking skateboards? So it's 80 out of 105. And we don't care about any of these other numbers when we're looking at that conditional probability. So in a sense, you've already been exposed to this, but now we're making it very explicit. Okay, probability of A, so such as probability of not liking skateboards. Okay, here we go. That's where that's found. It's going to be the probability of liking skateboards and liking snowmobiles. So let me go back to that. What this means is that, and this is where the language will get a little bit confusing. We can find our conditional probabilities here. We can also find this. This is not conditional probability. This is a probability of 2 events happening out of everyone. What's the probability out of 160 people that out of those 160 that they're going to like skateboarding and they're going to like snowmobiles? And that's going to be 80 of those 160. So it's actually a 0.5 probability. This is not the same as a conditional probability we just talked about, because it's a probability of liking both, not liking skateboards on the condition that someone likes snowmobiles. Because this 160 includes people who don't like snowmobiles. All right, we'll try and see that clarification as we move through. And we will have some practice problems with that. What's the probability that a person will like snowmobiles or will like skateboards? All right. And maybe I'll just run through this one. And you can, maybe I'll just give you a second to think about it. And maybe you can come up with your own answer before I run through it. So what's the probability that a person will like snowmobiles or will like skateboards? So not to step on your thinking, though, I'm probably doing that. We do want to think about this. Okay, yeah, I forget what my presentation looks like. So in this case, liking snowmobiles or skateboards, it doesn't matter if they like both, but it matters that they like at least one of them. And so from this two-way table, that's going to include everyone who likes snowmobiles, everyone who likes skateboards, but minus the people who like both. So the probability is technically, if I bring this down, it's going to be the probability if A is liking snowmobiles and B is liking skateboards, then here's what I can say. The probability of liking a snowmobile is 105 out of 160, plus the probability of liking a skateboard is 125 out of 160, minus the probability of A and B. Now, the probability of liking both is 80 out of 160. So the probability of both of this happening, I can just kind of, luckily it's all the same denominator. So 105 plus 125 minus 80 is, if I'm doing my math right, is that 150? All right. So there's our probability. So there we go. And just to see where that came from, that's the probability of those things. All right, now that can make sense because the complement to this would be someone who neither likes skateboards nor snowmobiles. And there's only 10 people who don't like either of them. So there we go.
Wait, I have a quick question.
Yeah, go for it.
So for when you're subtracting the probability of both, why did you only use 80 over 60 and not 105 over 160?
Okay, so this is the probability of A and B. And we find when two events are true, that's found here in the middle of the table.
Oh, I was looking at the table wrong.
Oh, okay. Oh, no worries then. Yeah. Now, another way we could look at this, just to show you that there's lots of different ways of interpreting this. If you like skateboards, so we have three outcomes that satisfy this condition. I like snowmobiles and I don't like skateboards. That works. I don't like snowmobiles, but I do like skateboards. That one works. Or I could like snowmobiles and skateboards. That one works also. So among those three conditions, I can find those right here. So if I add those up, 80, 45, 25, I get 150. And of course, it's out of 160. All right, I mean, that's just a different way of looking at it. But again, this formula holds especially when you have a problem where it's not, a two-way table isn't given, but they give you some probabilities. Okay, what's the probability that a person will not like snowmobiles or they will like skateboards? All right, I'm gonna see if you guys can find that and write the answer on the page, on the screen. And this is good. That is the correct probability. Remember, you can write it, I repeat myself a lot, but you can write it as a fraction, you can write it as a decimal. I think in this particular case, it's helpful to see it as a fraction, actually. So 135, just to make sure that's really clear, we're taking the probability of not liking snowmobiles, which is right here. That's 55 out of 160. And the probability of liking skateboards, we already used that in the last one. That's 125 out of 160. And I'm going to subtract the probability that someone likes both or meets both of those. So that's going to be 45 people out of 160. And when you do that, you do get the 135. So that's correct. Okay. So that's kind of your general addition rule introduction. And we'll talk about how other things come into play with conditional probability later on, especially with the general multiplication rule. So we do have special notation for conditional probability. So this is basically the term, the notation you need to know. This vertical line is a way of saying conditional. The probability of A given B. So in our previous example, the probability of liking skateboards among people who like snowmobiles, we could write that as the probability that someone likes skateboards on the condition or given that they like snowmobiles. And that was the one that we looked at before. Given that someone likes snowmobiles, what's the probability that they like skateboards? So that notation will be good for you to be aware of. I'll just keep moving forward. Oh, forgot I set that up. Okay. So find the following probabilities. You can just write this on the screen. What's the probability of not liking snowmobiles? Pretty straightforward on this one. Okay. So I'm going to have some more probabilities on here, but those are good. 55 out of 160. Probability of liking skateboards. All right. Doesn't seem like we've done anything new yet. And there you go. Yeah, 125 out of 160. So now what's the probability of not liking snowmobiles given that someone likes skateboards? Ah. Oh, let's see. Kevin's changing his answer. Okay. And there it is. So this is different from what the probability that someone doesn't like snowmobiles and doesn't like skateboards. If it was and, then we would say, oh, it's just 45 out of the 160. But this is conditional probability. So we're saying the probability of not liking snowmobiles on the condition that you like skateboards. So we're only looking at this column. And out of the 125, 45 of them don't like snowmobiles. All right, this might be a mental shift for you, but you'll get it. And last one, probability of liking skateboards on the condition that you don't like snowmobiles. Okay, I can agree with that. I know you might or might not be working through it as quickly, but hopefully we can explain it and help you get caught up. So now we're looking on the condition that you don't like snowmobiles. So we're looking at that row only and that you like skateboards. So that's 45. So 45 out of 55 is the probability there. Now this, I gave these two examples on purpose. Notice that the only difference between these two is I basically switched it from probability of A given B. And the second one I said probability of B given A. I just switched the A and the B for those last two problems. But notice that that changes the probability. And that's where conditional probability can get you mixed up a little bit. So make sure you understand that, you know, you have to evaluate each probability separately. You can't just do any shortcuts. Okay. Now, conditional probability, the probability of A given B. Another way of talking about this is the probability of A and B over the probability of B. So here we go. The probability of liking basketball on the condition of being female. So let me see, I should have some arrows. There we go. A and B. This is the probability of liking basketball and being female divided by the probability of being female. And that's evident right there. And this formulation of it is one that can be helpful to know from time to time. Okay. So now that leads us to our general multiplication rule. So before we had the rule that said the probability of A and B equals just the probability of A times the probability of B only if the events are independent. The general multiplication rule says it's a slight tweak. This looks like it's a very minor change, but it actually, I don't want to say it makes it super complicated, but it does change how we calculate it. Probability of A times the probability of B given A is the general multiplication rule. So we can use the general multiplication rule anytime, even the ones where the multiplication rule is acceptable. And we can see why right here. So we have this two-way table with independent variables. So I calculate it here. Okay. Let's see. Okay, this one's good. So we got a two-way table. It says that, and I made these numbers up, but it's preferring in-person versus preferring remote for juniors and seniors. All right, we got 50 students total. You can see how they're split between seniors and juniors and preferring in-person and preferring remote. So let's consider being a senior event A, and event B is going to be preferring in-person. So because the probability of B preferring in-person, so I'll kind of explain this. The probability of preferring in-person is found right here. That's our marginal total. And that's just 20 over 50. The probability of B given A, now A is being a senior. So now I'm going to be conditional on this, but notice it's going to be 16 out of 40, and that's also 0.4. All right, so it doesn't matter whether we use the general multiplication rule or the multiplication rule in this case. These are set up to be independent. Okay, so in this case, we're good either way, but we will more likely have scenarios where the variables are not independent. So we need to use conditional probability. So what's the probability that someone will be a male who likes football? Okay. Let me go back to this real quick. So you can see the two-way table right here. I think the calculation that I illustrate next will kind of help go through it. The probability of being male, so we'll talk about just that part right there. The probability of being male is 48 out of 100. The probability of liking football, given that you're a male, is, let's see, on the condition of being male, it's going to be 20 out of 48. And that's where that comes from. So now we get to the last part. This general multiplication rule says I'm going to take the probability of A times the probability of B given A, and we have both of those now. And I can multiply them together. So 48 out of 100 is the probability of being male times the probability of liking football given that you're a male. And that gives us a probability of A and B. Final answer right here. Now this is one you might think it's not necessary because we already have the numbers. We could just look at the two-way table and see that it's 20 out of 100. But this does help to illustrate why the general multiplication rule works. We're basically canceling out the 48s. All right, I'm going to pause right there and ask if there are any questions. Okay. So at this point, we're just going to do some practice with these ideas. And hopefully by the end, we will feel comfortable with the general addition rule, general multiplication, conditional probability. And, maybe kind of a mental approach to this is treating each one of these like it's a puzzle. And that might not do anything for you, but maybe just kind of thinking through these math problems, these statistics problems more specifically, as puzzles will help kind of make it more interesting. So suppose the probability that a US resident has traveled to Canada is 0.18. to Mexico is 0.09, and to both is 0.04. What's the probability that an American chosen at random has traveled to Canada, but not Mexico? And you can see there are other possibilities. So for a problem like this, I'll go ahead and tell you the best thing to do is to set up a two-way table. So this is going to be something you want to get very familiar with doing. So I've got Canada. And I'm just going to put yes or no. That means yes, I've traveled to Canada. Yes, no, I have not traveled to Canada. And then we're going to have Mexico. Yes or no. The probability that, and these are all US citizens that we're talking about, the probability that a US resident has traveled to Canada is 0.18. So this is my marginal probability, and we're going to have 100% for the total. The probability that someone has gone to Mexico is 0.09. And again, that's the yes for the Mexico row. And the probability that they've been to both is 0.04. So that means, and that's going to go right here. So I can fill in the rest of this table based on just this information. I know that my row marginal or conditional totals have to add up to the marginal total. So that means right here, this has to be 0.05. Same thing in the column. If 4% have been to both and 18% have been to Canada, that means to make up the difference, 14% must have gone to Canada, but not Mexico. And now I also know we can do a couple of things here. I know that this marginal total has to add up to 100%. This marginal total has to add up to 100%. So I can create those numbers. That's going to be 0.82, and this is going to be 0.91. So this is good so far. Now we have a couple of ways of solving for this last one. I know that all four of these have to add up to 100%. So I could do that, but maybe an easier way is just going across the row. I know that the two conditional totals have to add up to 0.91. So that means it's going to be 0.77. If I did it right, these two should add up to 0.82, and they do. So it seems like we're given very limited information, but we actually have enough here to set up an entire two-way table. Okay, so now we can answer these questions. The probability that someone has traveled to Canada but not Mexico. Yes, Canada, no Mexico. Well, there it is, 0.14. Traveled to either Canada or Mexico. What's that total going to be? Or what's that probability going to be? Keep in mind right here that we are using our general addition rule for this because our general addition rule is used for or. So A or B, the probability of that's going to be the probability of A plus the probability of B minus the probability of A and, am I going to have room? B. All right, so I'm going to have the probability of A, meaning going to, in this case, going to Canada, is 0.09. The probability of B, Canada should have been the 0.18. Mexico is the 0.09. The probability of both is this, so 0.18 plus 0.09 minus 0.04, which is and going to both. And that gives me the total, and 0.23 is what I got as well. So there you go. Good job. And if you weren't able to get it, hopefully seeing that is helpful. So I'll go ahead and write this in, 0.23. And then the probability of not having traveled to either country. What's that going to be? There you go. The answer is indeed 0.77. And we can think of this two different ways. I mean, it's right here. I've not been to either country. There's my answer. Also, we just found out that if you've traveled to either Canada or Mexico, it's 0.23. So obviously the complement of that. So the probability of Canada or Mexico complement. There you go. Okay. So I just have a few problems, just like yesterday. I think it's really good with probability just to look at a bunch of different problems and figure it out from there. So what we have here is another two-way table, and we're going to answer some questions about it. But what we're missing in this table, well, maybe you can tell me. What else do we need before we can start answering questions about this table?
Totals.
Totals. We need our marginal totals. So I can put a total here, a total here. We can add that up. So if I add down the row, I get, what is that? 80, 90, or sorry, 40, 50, 62, 0.62 right here, 0.38. All right, adding across, we can do this pretty quickly. That's those numbers right there. Now this should add up to 100%, and it does. So we're good. So we will need that before we can answer this completely. What's the probability that a randomly chosen voter prefers the death penalty?
.38.
Point.
Oh, prefers it?
Yeah, prefers it, yeah.
0.62.
You got it, 0.62. Yeah, so favor, we're looking at the total right there. Very good. I'll go ahead and write it down. What's the probability that a Republican favors the death penalty?
.26 out of 0.62.
I think it's probably set up a little differently, but you have the right idea. Or wait. See, sometimes the wording is very tricky. So that, sometimes I would say this is maybe some questionable wording. Just in my head, I'm not saying this is right. In my head, I read this as, what's the probability of a Republican, that's the condition, favoring the death penalty? But I think I could see it if I change my perspective on how I read it. I could see the death penalty being the condition and the Republican being the conditional part of the probability. So we can look at it two ways. If being a Republican is the condition, then it's 0.26 out of 0.30. We can figure that out. If it's the way that Kevin just said, if preferring the death penalty is the condition, then it's 0.26 out of 0.62. So this is one of those very almost ambiguous questions. And you can see where language can sometimes get in the way. So it's almost like one of those pieces of art where it's like, do you see the old lady or the young woman? Is that resonating? Okay, so let's just scratch that one. I think the next one's much more clear. What is the probability that a voter who favors the death penalty is a Democrat? I think I only have one way of reading this question.
Is it 0.12 out of 0.62.
There you go. So now we're saying the condition is, I think it's very clearly stated that the condition is that someone favors the death penalty, and what's the probability among those people that they're a Democrat. So there it is, 0.12 out of 0.62. Of course, we can calculate that. And 0.194 basically is your probability. So a candidate thinks she has a good chance of gaining the votes of anyone who is a Republican or in favor of the death penalty. What portion of the voters is that? So 0.66, and just to show how we got that, what did you do to calculate 0.66?
I got the total of Republicans added to the total of the people who favor the death penalty and then subtracted both, which is 0.26.
Okay. So there we go. Those three numbers right there. It's going to be probability of Republican plus a probability of death penalty. That means yes in favor of, minus the probability of both. Republican, the D makes it look like Democrat, so I should have maybe picked something different. And death penalty. Anyways, yeah, you can go through it. So it's 0.3 plus 0.62 minus 0.26, and that is your 0.66. Very good. So you can see, maybe if I haven't made it very clear yet, if you're ever looking at an OR situation, this is going to be your general addition rule. If it's an AND situation, that's where it's going to be general multiplication rule. Okay, let's move ahead. 20% of cars that are inspected have faulty pollution control systems. The cost of repairing a pollution control system exceeds $100 about 40% of the time. When a driver takes her car in for inspection, what's the probability that she will end up paying more than $100 to repair the pollution control system? I'll just let you guys think through this one. Let me know when you have an answer. And again, I hope I'm not cutting off anyone's thought process if they were like really thinking through this problem. This is almost a question ahead of the times. Maybe I should have waited to ask this question, though it is in your book in this chapter. This is what you're probably looking for, and what you might be trying to create is a two-way table out of this. And if you're trying to do that, I applaud you. It's actually not necessary for this problem. And so maybe to explain this question, we are going to talk in a little bit about, not today, but another, we're going to talk about tree diagrams. All right, and we have conditional probability that can be diagrammed out like this. And the only thing that's important is that this is another way of thinking through conditional probability. And on the condition that someone actually is flagged for a pollution control problem or faulty pollution control system, that happens 20% of the time. So that's 20% of the time that happens. And then on the condition of that, this 40% is already a conditional probability. So that's where you might be getting thrown off. Okay, so already on the condition of repairing a pollution control system, you wouldn't go in if there's no problem. So we already have that condition met. And it exceeds $100 about 40% of the time. So I'm going to say this is the 40% of the time where it's over $100. So really all we have to do is multiply these two together. 0.2 is the probability of a faulty system. Let's put that. And the probability of, I'll put expensive, given that it's faulty, is 0.4. And now we can just multiply it together. It's 0.08. So I imagine some of you weren't able to come up with an answer because you were trying to think through it and thinking it was more complicated than that. So this is maybe a question that will, in retrospect, you'll be able to put it in its proper place. Okay. So this one, I'll kind of run through this at the beginning at least. the soccer team shirts have just arrived in a big box and people just are grabbing them, looking for the right size. The box contains 4 medium, 10 large, and 6 extra large shirts. No smalls. All right. You want to find the medium for you and one for your sister. Find the probability of each event described. Okay, so we're going to start this off. It says people just start grabbing, and we're going to assume that we are the first one to start grabbing. And let's see what we can do here. This is sampling without replacement. This is, we have to change our probabilities as we go through. So it'd be great to say, oh, the first one is not medium. So we're looking for medium for 2 people. It'd be great to say, oh, well, we get not medium and not medium multiplied together and we're done. But now we have our probabilities change. So how many shirts are there originally? 4 plus 10 plus 6. We've got 20 shirts. So I'm going to write it out this way. The probability of getting a not a medium. So medium is what we want. So the complement of that. That's the first thing. And now it's going to be the probability of not getting a medium again on the condition that we already didn't get a medium. Does that make sense? So now I can figure this out. I can figure out the probability of getting a medium, not getting a medium rather, is going to be, if there are 4 medium, that means there are 16 not. So 16 out of 20. Now the next time around, I also didn't get a medium, but I've already taken out another shirt. Maybe it's large or extra large. So there's only 15 non-mediums at this point, and there's only 19 shirts. So it's going to be times 15 out of 19. And there's our probability. We can multiply that together. And you can confirm, see if you got the same number I did. That look good for you? Okay, thumbs up. So now we have another thing, which is the probability that the first medium shirt you find is the third one you check. All right, so this is something we can do. Probability of, so we want to get not a medium, then a medium. We already found the probability of getting 2 not mediums in a row. So I'm just going to add to this. So I'm going to copy what I already have. Not a medium and not a medium given that I didn't get a medium to begin with, and getting a medium on the condition of, I'm just going to put not medium. All right, because I don't want to have to write out something really too complex. So on the condition that I never got a medium, what's the probability of getting a medium the third time? I'm saying medium so much, it's starting to not sound like a real word. Okay. So we already know it's going to be 16 out of 20. And then it's going to be 15 out of 19. What's the probability the third time of finally getting that medium?
$14 out of 18.
There it is, 14. Oh, well, 14. So in this case, we actually are getting a medium. It is out of 18. It's not going to be 14. All right, Aries, have a good one.
Thanks, you too.
So how many mediums are in the box at this point?
It'd be 4 out of 18.
There it is, 4 out of 18. So we're saying we actually succeeded on the last shirt we pulled out. We did find a medium. All right. So now we can multiply that out. And I'll just put the number up there so you can double check. And if I got it, if most people aren't getting the same thing as me, then I made a mistake. And keep in mind, you're learning the important statistics. So next time you're grabbing something randomly out of a box, you'll know the probabilities. All right, this is where statistics is applicable in the real world. Okay, the next one, probability that the first 4 shirts you pick are all extra large. Maybe we can just talk in theory about how to do this one, because we already have this main idea. So we can, well, I had a question saying, we'll just run through so I'll run through this problem in full. So the first 4 shirts we pick up are all extra large. So let me get rid of everything on the page. Maybe I'll keep the first few problems up, but all right. So we're gonna focus on this one. The first 4 shirts we pick up are all extra large. So that means the first, we wanna find the probability of 4 things happening. I pick up an extra large shirt, and next I pick up an extra large shirt on the condition that I got an extra large shirt, and that I get an extra large shirt on the condition I got 2 extra large shirts. It's going to be a bunch of X's. And I get an extra large shirt on the condition I got 3 extra large shirts already. Okay. There have been a lot of questionable things that I've written on the screen today, if you read this out of context. So we just have to make sure that we understand. We're talking about statistics here. Okay. So now we need to go through and figure out just each one of these probabilities. And it's not as difficult as it seems. So I'll write the probabilities down at the bottom. So if there are 20 shirts to begin with, and we're looking at only extra larges, we start off with 6. So I start off with 6 out of 20. And we're going to see there's a pattern to this as we go through. So that's the first one right here. Now I want to find the probability of getting an extra large, given that I already pulled out an extra large. So what is the next one going to be?
5 out of 19.
5 out of 19. There's only 5 extra larges left, and there's only 19 shirts left. Times
4 out of 18.
4 out of 18. And so if you're not sure where that came from, now we're going to do the probability of getting the next shirt being extra large on the condition we already pulled 2 out. And then the last one, we should see a pattern here. What's the probability of getting an extra large on the condition we already pulled out 3?
3 out of 17.
3 out of 17. There it is. That is what you can multiply together. Essentially, this is just 6 times 5 times 4 times 3 over, and this is how I'd actually plug it in my calculator, 20 times 19 times 18 times 17. So I just do all the numerators multiplied together times divided by all the denominators multiplied together, put parentheses around it. We can go ahead and get that number. And how about this time you guys can write that on the screen? Just anywhere there's room, you can put your answer. Okay. I got the same thing. Okay. So any questions on this with these so far? I'm about to erase everything on the screen. Okay. So the last one is these at least problems, at least one. So now we have to think through this differently. The only way we fail at this is if we pull 4 shirts out and none of them are going to be medium. So I will write out just the notation for this. I want to get not a medium and not a medium on the condition of not a medium, and not a medium on the condition of 2 no mediums, and not a medium on the condition of no mediums drawn so far. All right, so let me see. There's 1, 2, 3, 4 shirts drawn from the box. And that means if that's what happens to me, then I have failed. I did not get at least 1 medium. So I want to get the complement of this entire thing. And so now I can kind of run through. I'll just start plugging in numbers at this point. And I apologize if you guys are getting this and you're like, oh, why don't we see different types of problems? But I feel like it's helpful to run through it in its entirety. All right, so the probability, we've already done part of this. We already know that we start off with a 16 out of 20 probability of not getting a shirt. Not getting a medium, that is. What's the next one? We can just quickly do this.
$15 over $19.
All right, the next one.
$14 over $18.
And the last one.
$13 over $17.
13 over 17. There we go. That's the probability of getting no medium shirts. And because we're doing the complement of this, here's what I'm going to do. I'm going to do 1 minus that probability. Okay, so now you can plug that into your calculator. All right, and right on the screen, what you get is your answer. The question really is, or the main takeaway, because as far as the actual calculator work on this, it is pretty straightforward. And you might find it helpful just to worry about this part of the calculation first. And once you get that number, do the 1 minus whatever you get. So this is, everyone might have their own way of plugging this into the calculator that makes sense for them. But here's the thing. Everything leading up to this calculation is the main concept, the main takeaway. So are there any questions on this? All right. And I know that this right here, this expression makes it look way more complicated. And maybe it's necessarily complicated. Maybe you feel like there's a way you could run through it in your head that makes a lot more sense, but this is the notation you need to be comfortable with. Okay, so let's look at, I don't know how many more problems I have for us today. Okay, just 2 more. There we go, that's not too bad. So 56% of all American workers have workplace retirement plans, 68% have health insurance, and 49% have both benefits. We select a worker at random. So real quick, before we start trying to answer any of these questions, what should we do for this problem?
Should we do a 2-way table?
This is one where it would be appropriate to create a 2-way table. I won't fill this in. In fact, that'd be great if you guys could fill it in. I will just put the 2-way table right here. I didn't make it very pretty, but we can work with it. So we've got retirement. I'll just put R for retirement, yes and no. And then health insurance, H, yes and no. So see if you can fill in that table with the appropriate numbers. And once you have, we can get all 9 of those tables filled in, those cells. All right, good job, guys. That is all correct. And again, I know not everyone wrote on this 2-way table. So just to make sense of where this came from, the 68% and the 56% here, these are the marginal totals, because we're talking about all workers. Out of all workers, 56% have a retirement plan. That's where that goes for marginal totals. Now the health plan, 68% have health plan. So that's where that goes as a marginal total. And then we get into the middle of the table where it says 49% have both. And so this is, yes, they have retirement, yes, they have health, and that's where that goes. And that's really the only three numbers they give us. But then we also know that we have to have 100% of people accounted for. So that goes in the bottom right. And those four numbers, that's really all we need. So now the conditional totals right here have to add up to the total at the end of the column and at the end of the row. So 49% plus 7% equals 56%. And then we can go across the row. 49% plus 19% equals 68%. And we can just keep doing that for the two other rows. These two have to add up to 0.32. These two have to add up to 0.44. Now, I guess one other thing I should mention, because I haven't said it yet, is these two have to add up to 100%. So that's where the other two numbers came from. The 0.32 and the 0.44 comes from figuring out how the marginal totals will need to be distributed to add up to 100%. All right. So now we have the two-way table. It should be, that hopefully is the hardest part of this problem. So let's look at it. What's the probability that this random worker has neither employer-sponsored health insurance nor a retirement plan? And you can just say it out loud if you know the answer.
25%.
25%. So we're saying no health insurance, or sorry, no retirement and no health insurance, which is 25% right there. So I'll just write that in, 0.25. What's the probability that he has health insurance if he has a retirement plan? Ooh, this one's a little tougher.
I got 0.125.
Let me see. I got a different number.
I got 0.875.
I got a different number. Wait, oh, you know what? I personally made a mistake on that. So my number wasn't correct. So let me see if mine matches what you just said. See, 0.875 is what you said. That's what I got as well. Okay, so tell me how you got 0.875.
I got the total of the people with a retirement plan, and then just got of that total who had a health insurance.
Okay, so I think, Lily, you just did the probability of not having health insurance. And so I think that's the only thing that you mixed up, but you had the conditional part of the probability correct. Okay, so we are conditional on that someone has a retirement plan. And so there we go. It's 49% out of 56% does give you the 0.875. The idea here is if I only looked at that 56% of the population, I randomly drew someone, I'd have an 88% chance that that person also has health insurance, if that wasn't clear before. So I'll go ahead and write that in, 0.875, and maybe I can just put over here on the side, 0.49 out of 0.56. Are having health insurance and a retirement plan independent events? I'll just let you think about this one for a minute, see if you can come up with an answer. So there's different ways we can look at this question to answer it. And maybe the first way I'll talk about it, and we'll see how many ways I go through this. Actually, I didn't want to erase that. I wanted to erase this. All right, so we do have our general multiplication rule. Sorry, our regular multiplication rule that says the probability of A and B equals the probability of A times the probability of B if they are independent. This is on the assumption that they are independent. So here's what I'm going to do. I'm going to plug these numbers in. The probability of A, and I will say the probability, I'll rewrite it this way. The probability of retirement and health insurance has to equal the probability of getting retirement times the probability of having health insurance. And that's only true if they're independent. All right, I've said that enough. Hopefully we're good with this setup. I already know the probability of and. It's right here. It's 0.49. The probability of retirement is 0.56. The probability of having health insurance is 0.68. So I'm going to multiply out on the right side. And I get 0.3808. If these were truly independent, we would see these two equal each other, but they're not. So therefore, they are not independent. Does that make sense? Okay. And I know this it's a little bit tricky, kind of trying to think through that. Maybe that's actually good enough for now. There are other ways we could think through this, but that's maybe the condition we're going to come to and focus on. The next one's actually a little bit easier, and I will let you guys see if you have a quick way of finding this one out. Are having these two benefits mutually exclusive?
No, right?
They are not mutually exclusive.
Yeah.
There. Yeah, and I had to think through it too, the phrasing. But that's correct. They are not mutually exclusive. Does that just seem right to you, or do you? What's your reasoning?
Just that you can have both at the same time.
That's perfect. There you go. So remember, the question to ask yourself is, if things are independent, I'm going to come back to mutually exclusive. But for independent, the idea is, does having the first event happen change the probability of the second event? And we can see you're more likely to have health insurance if you have retirement. All right, so that does change the probability. If one is true, then the other is more likely to be true. So they're not independent. So for mutually exclusive, the question is, can both be true at the same time? And we only need to check one spot in this two-way table, and that's this top left. It's not always in the top left. You have to be careful about this. But in this case, having both of those, if they're mutually exclusive, this would have to be a 0. Okay, but 50% of people have both of these, so we know you can have both of those events true. So they are not mutually exclusive. And remember, another way, we've seen this in the past, the probability of A and B, if they're mutually exclusive, is 0. So that's the main takeaway on that. All right, so this is, granted, kind of some mind-bending stuff that we have to talk about, and every single question you kind of have to wrap your head around it for a little bit before you can just straight up answer it. If we need to come back to this, please just stick around. We can go over this stuff again, but we have just one last question. Are party affiliation and position on death penalty independent? So you guys can look at that one for a minute and think through it. And I fully imagine some people out there are circling around an answer. Maybe you feel somewhat confident about an answer you've come up with. I'm going to put the marginal totals real quick. So 0.3, 0.36, we've already done this, and 0.34. This adds up to 100%. This is 0.62, and this is 0.38. So we have two ways of doing it. we can remember that it's only independent if the probability of, I'm going to say, and it doesn't matter which one we pick. So I'm going to say the probability of Republican and favor, I'll use favor this time around. So favor and Republican, the probability of both of those has to equal the probability of Republican times the probability of favor. And if that's true, then they are independent. So I already know that this is 0.26. Probability of Republican is 0.3. Probability of favoring this is 0.62. And if I multiply that out, 0.3 times 0.62 is 0.186. So because they don't equal each other, that means they are not independent. And here's the real world interpretation. So we just did some numbers, we did some calculations, that's all well and good. The real world interpretation says that we are more likely to find someone support the death penalty if they are a specific party affiliation versus another. The probabilities are not the same. So we can see, I could look at this a different way. So let me kind of just show you one last thing, and then I'll show you your homework. So if I look at the probability of this row and then the total, the probability of being in favor of this is 0.62, right? So that's 0.62 out of 1. So the probability of being in favor is 0.62. The probability of being in favor of this, given that you're a Republican, is 0.26 out of 0.3, which is 0.867. These two have to be equal if these are independent, because that means that party affiliation has no impact on the rate of favoring the death penalty. But it looks like it does. If you're a Republican, you favor it way more than the overall population. And we could look at the Democrats and the others to kind of see where they fall as well. I could have picked Democrats right here. I'm not trying to pick on one party. So I could have switched that out with Democrats and tested them. But that's the idea as well. All right. I know there's a lot of stuff to think about through this. Like I keep saying, if you need to go over anything with me, please stick around. There's your homework for tonight. It does say we're going to review for the Unit 5. Okay, we're going to review tomorrow, but you know what tomorrow's plan is. Choose your own adventure. So besides that, have a wonderful day. I kept you here until the very end of the day. I appreciate you sticking around.